Hello students, welcome back. Previously in section 1, we defined the rational function and then we went through the domain problems. Domain problems are always important in college algebra, so please remember those. Now at the very end, we talked about a classification of asymptotes, like these. Horizontal asymptotes, vertical asymptote, slanted asymptotes, and those are linear asymptotes, and the final example is curved asymptote or nonlinear asymptote. Basically, we're going to cover horizontal asymptote in section 2, vertical asymptote in section 3, and these two in section 4, along with some reviews on previous materials as well. Now let's come back. Horizontal asymptote, slanted asymptote, and curved asymptote. These three are all about the end behavior. As I move to the right or to the left, the graph is getting closer and closer and closer to the asymptote. Whether the asymptote is a horizontal line, slanted line, or a curve, that depends, but in any case, it's an end behavior. So that's something we're going to discuss first. And then in section 3, we are going to talk about vertical asymptotes and some other things as well, and those are going to be local behavior. Not toward the right end or toward the left hand, but locally around x equals to 1 or x equals to 3 in this case. Okay, local behavior that can wait. Let's go to end behavior first. Let's take care of some theoretical foundation first. We say a pair of real functions f and g are asymptotically equivalent if the ratio f of x over g of x gets pretty close to 1 as the absolute value of x gets really large. Now, if the ratio is equal to 1, then f and g are the same. If that's close to 1 but not exactly equal, then they're not exactly the same, but they're going to behave pretty much similarly. And that's what this asymptotic equivalence is all about. The precise definition requires calculus, so we're not going to go there. Instead, we're going to focus upon how to use it. And this is very, very simple. All you have to do is to take the highest degree terms from the numerator and do the same for the denominator and simplify. If you do that, you're going to get a power function over power function. Eventually, you're going to get a single power function that shares the same end behavior as the original rational function. Now, the original rational function is going to be really complicated in general. The power function, on the other hand, is simple and we know already. So we can use the behavior of the power function, which we already know, to describe the behavior of the rational function. Basically the same thing we did for polynomials. A little bit more complicated, yes, because we have two polynomials this time. Here's an example. We have something really complicated like this. And then let's look at the numerator first. This is something we had been doing in polynomials. Take the highest degree term only and then compare. In small scale, they're not the same. In medium scale, already we can see some appropriate behavior. In large scale, they become kind of indistinguishable. That's a visualization of asymptotic equivalence between one and the other. They share the same end behavior. Now you can do the same thing for the denominator. Again, the same idea, take the leading term only, and then in small scale they are radically different, but in large scale, look at these graphs. They behave pretty much the same. Even in medium term, you can see similar kind of behavior developing. Now, what if you put those two together and form a rational function? Let me expand the font a little bit here. Okay. Take the leading term of the numerator and the leading term of the denominator and simplify. We get a single power function, negative 2 over x. That's the red graph. And the original graph here, that's brown, and in small scale, they're radically different. In larger scale, on the other hand, they behave pretty much the same. To the right here, and also to the left there. And also, look at the index here, 0.2, 0.4, and vertically it's actually very small, so the difference is actually very, very small for these. One more thing, look at this power function and x in the denominator. So if that gets really, really large, then the entire fraction is becoming pretty close to zero because denominator is getting humongous. And that's what we are looking at here and also there. The graph is getting closer and closer and closer to the x-axis, or y equals to 0. And that is your horizontal asymptote in this case. In general, you're going to get this kind of example. Or excuse me, that was the example. In general, you're going to get this kind of summary. When the numerator and denominator have same degree, then we have x to the 0 power here. So this one just drops out, and we just have a constant am over bn. And we get a horizontal line. Now, what if the denominator has higher degree? In that case, we have some leftover x to whatever power in the denominator, as the previous example we just saw, and that's becoming humongous, so the overall fraction becomes so small it becomes 0 in the end. So the horizontal asymptote is y equal to 0. That's the example we just saw. Now the third case, what if the numerator has higher degree? In that case, there's some leftover in the numerator, x to the n minus n power, and that's going to blow up to positive or negative infinity, depending upon the direction and also depending on the sign of this. So we have no horizontal asymptote. So remember the summary and use the summary to answer these questions. Stop the playback and try on your own. Did everybody try? How about the first problem here? You can plot it, but even without plotting, you can find out the horizontal asymptote. If you take more than 10 seconds, you're doing it wrong. It's really, really simple. It should be simple. So how do you get that? Simply take the leading terms, highest degree terms, and then disregard the rest, like this. And then what do you have? We have 5x squared over 2x squared. After simplifying, you get 5 halves, a constant. And that is going to be your horizontal asymptote. Here's a visualization. In small scale, you don't see any resemblance, but in large scale, to the right end or to the left hand, you can clearly see the asymptotic behavior. There goes your horizontal asymptote. And the power function that shares the same behavior is constant function 5 halves. How about the next problem here? Again, if you take any more than 10 seconds, then you're doing it wrong. It falls to this category, right? The denominator has higher degree. Now, how about the power function that shares the same end behavior? You can easily calculate it through the asymptotic estimation. Simply take the new term of the numerator and the leading term of the denominator, put it together, put those two together and simplify. You're going to get 1 over 2x squared, and that's going down to 0 as x gets large. The horizontal asymptote is y equal to 0. Here's the visualization. In small scale, the original function, blue, and the power function, 1 over 2x squared, red, and the horizontal asymptote, y equal to 0, are completely different. But in the second picture, toward the right end or toward the left hand, they behaved pretty much the same. That's what this horizontal asymptote is all about. Excuse me. Sorry about the typo. Horizontal asymptote. Now, blue, red, and green are 3 different functions. You see? Look at this especially. There are 3 different functions. They are not the same. Now, we used equality here. So this expression, that expression are the same. Okay, they're the same. And then these 2 are the same. But that's not an equality. That 2 is not an equality. We're talking about different functions. So we have blue, red, and green. They're 3 different functions, but they all share the same end behavior. To the right, to the left. How about this? Again, if you take any more than 10 seconds, you're doing it wrong. It should be really simple, really easy. Where does this fall? It falls here. No horizontal asymptote. Numerator has higher degree. As for the power function that shares the same end behavior, again, you can use the asymptotic estimation like this. Take the highest degree term in the numerator and highest degree term from the denominator, and then simplify. You get it y equals to 2/3 of x. And here is a visualization. Picture them together. Blue is the original, red is the power function, linear power function, y equals to 2/3 times x, and you can see they share the same end behavior. Now, is this an asymptote? The answer is no, actually. You can clearly see it from here to your right. Blue and red are becoming kind of like parallel. They're not really merging. Here too, but it's a little bit more visible over there. It is possible to get true slanted asymptote, but that'll require a little bit different technique. But if you do get it, you're going to get this kind of picture. Please note that this picture and the previous picture here are on the same scale. X going from -10 to 10, about 11. Y going from -20 to +20. Same scale, but here we have merging, clear merging. Here we have parallel. We're going to talk about how to calculate this slanted asymptote in section 4. For now, let's stick to horizontal asymptotes only. Next example here. Okay, all right. How about this one? Which category is it? 1, 2, 3. It's going to be 3. So no horizontal asymptote because the numerator has higher degree. If you want a power function that shares the same end behavior, you can use this asymptotic estimation. 2x to the 4th power with x squared, so we have 2x squared. And here we have those visualization. In this large scale, -20 to +21, maybe 22 or so, you can see the graphs, blue and red, share the same end behavior. You can clearly see that. Here, -4 to +6, what +5, and they behave radically different. Now, is this red an asymptote? The answer is no. You'll have to use similar technique that I talked about before, relate this to this polynomial division, but if you do that, you're going to get this kind of picture. Same scale here, but here you can clearly see we have nice merging. Not here, even in same scale. As a matter of fact, you can see the asymptotic behavior from here in smaller scale. We are going to talk about these in section 4. For now, let's just stick to horizontal asymptotes only. Okay, final example here. How do you get that? If you take any more than 15 seconds, you're doing it wrong. Do not try to break apart all these parentheses. That's going to take you 15 minutes. I just told you if you take any more than 15 seconds, then it's not the right method. So how do you handle this asymptotic estimation? Take the highest degree term, and you can do that for each factor. Like this. Take the highest degree term for each factor and disregard the rest. Put those together and you're going to get 4x to the 4th power over 3x to the 4th power. After simplification, you get y equals to 4/3, and that is your horizontal asymptote. In small scale, they are completely different, but in larger scale, you can clearly see the asymptotic behavior. Okay, so much for the end behavior, the elementary end behavior, and the horizontal asymptotes. We are going to come back and discuss section 3, local behavior, in a separate video.